The question we are we're discussing is the Project Euler question problem 7. What's it? 10,000 first prime number. By listing the first 6 prime numbers 2, 3, 5, 7, 11, and 13, we can see that the 6th prime number is 13. What's the 10,001st prime number? So, and first we should know what are the prime numbers. The prime numbers are the numbers that are only divisible by 1 themselves. So all numbers that have the same condition except 1, that the number 1 itself, are prime numbers. So for example, 2 is a prime number, as it is divisible by 1 and 2. And 3 is also a prime number, because it's only divisible by 1 and 3. In other words, we can say that the prime numbers are the numbers that are only divisible by 2 positive integers. So, by knowing these things, we are trying to find a way to get if a number is prime or not. And we know 2 things: that all integers are divisible by 1. So we don't need to check that, because they are all divisible by 1. And they are all divisible by themselves. Like number 10 is divisible by 10, number 20 is divisible by 20. So we don't need to check for that. So all we need to find out is that is there any other number between 1 and that number that divides the number or not. If there is, that number is not prime. For example, 13 is not a prime number. In 13, the modulo of 13 and 1 is 0, and also the modulo of 13 and 13 is 0. So the 13 is both divisible by 1 and 13. But there are more numbers that 13 is divisible to. For example, 5, 2, and more. So 13 has more than 2 numbers that its modulo to them is 0. So what's the shortest way to find if a number is prime or not? To do that, for example, if we try to do it for 35, we look for the numbers that are between 2 until the square root of 35. Because if a number is divisible by 35 and it's greater than its square root, and there is surely another number less than its square root that's also divisible to. If you want to know why is that, like for example, the number n is divisible by a, and we know that a is greater than the square root of n. So n divides, if we divide n by a, there's a number b. So we know that b times a is equal to n. A is greater than the square root of n. So b should be less than the square root. If both are greater than the square root, so we want to prove that. I'm gonna prove this. So we say that if both a and b are greater than the square root of n, what will happen? A times b is greater than a square root of n times a square root of n, which is greater than n. So a times b cannot be equal to n. So if there's a number greater than the square root that is divisible by n, that divides n, there is surely one other number that's less than the square root that divides n. So we don't need to check the numbers that are greater than the square root. We only need to check the numbers that are between 2 and the square root of that number. And what will happen if the number is a square number? And is a perfect square, like 4. So for that, we need to, so instead of finding the square root of 10, we find the square root of n plus 1, just to make sure that if a number is a perfect square, we also consider its square root. So here I define the function name is prime. Why I choose is prime because it's more nicer when you say if is prime. It's more meaningful. So I check if a number is less than 2. If a number is less than 2, it means it's 1, 0, or a negative number. So it's not a prime number, because prime numbers are only defined for numbers that are positive, and 1 is not a prime number. And then I will go through the numbers between 2 until the square root of n plus 1, of number plus 1. Because I didn't want to use the square root function. I used I times I is less than the number plus 1. It's the same thing. And then I will check if the modulo of the our number and I is 0, which means that that number divides I, then it returns false, because that number cannot be a prime number. If nothing is returned up there, so it means that no numbers except 1 and the number itself can divide that number, then it's true, and that number is prime. So, for example, let's see what will happen for 35. It goes between 2 until 6. Oh, we check. And 35 is greater than 2. 35 and the modulo of 35 and 2 is 1. The modulo of 35 and 3, what is that? 3 and 5. 3 and 5 is 8, then yeah, that's 2. And 35 modulo of 4, it's 32, it's 3. 35 modulo of 5 is 0. Then we don't need to continue, because when the modulo of that number and I is 0, then it returns false, so it's not a prime number. But for prime numbers, it will return true. And then here is the main function that I defined the counter, and that starts from 0 until that number, 10,001. And then there's an I that actually is, yeah, and it's a brute force. And that goes from 1 until 10,001. No, I mean, it goes up until find the 10,001st prime number. And then for each number, it checks if it's prime or not. If it's prime, it will increase the counter by 1. So it means that we find 1 more prime numbers until the counter is 10,001. Then we will continue. And then it prints out that number. So if I run it, it will give me the number 104,743. And this is the right answer.